Hello, and welcome to the latest installment in the Physics 140 pre-class lectures. Today's lecture is going to be less about physics and more about a review, at least I hope it's a review, of some of the math that you're going to need to be successful when we start looking at kinematics in 2 dimensions, and for that matter, any vector in 2 dimensions. A vector in 2 dimensions can be specified by the x component and the y component. It can also be specified by the magnitude and direction. I want you to be able to convert from information in x component, y component form to magnitude and direction form. And vice versa, I want you to be able to start with magnitude and direction and convert it into x components and y components. That's the goal of this lecture. Now, I approach this in a very individualistic way, an idiosyncratic way that I think kind of gives a one-size-fits-all approach. And I will be sticking with this approach throughout the semester. If this is different from an approach that you've seen before with which you're comfortable, I hope that you understand how I'm doing it, and if you still want to approach problems the way you were taught before, and if you're comfortable with it, and if you understand it, by all means do so. What I will be describing is not the only approach, but I think it's a good approach for teaching purposes, for pedagogical purposes. It's just, you do it this way, and this will apply to all situations that you have to worry about. That's how I'm approaching it. Now let's make sure we understand some of the terminology. I refer to an x component or a y component, for instance. What exactly do I mean by that? On the screen, you see a standard Cartesian coordinate system, x-axis horizontal, y-axis vertical. And the arrow in red represents a vector. I don't know if it's displacement, velocity, acceleration, some other vector. The important thing here is it's a vector. The very tip of the arrow can be described with Cartesian coordinates, an x-coordinate and a y-coordinate. The x-coordinate is the same thing as the x component, and the y coordinate is the same thing as the y component. Also, another way of looking at it, you can see that the red arrow has kind of been projected a little bit onto the x-axis. If it were to cast a shadow solely on the x-axis, it would be the length that you see shown by the bracket, and that is also the same as the x-coordinate, and that is the same as the x component. We see another example of an x component, but now this value is negative. The arrow, the vector, has a leftwards trend. The x component, being in quadrant 2, is a negative quantity. That's okay. We have to be able to handle situations where the x component is negative. It's going to happen. Just don't forget that minus sign. But otherwise, everything else it's the same idea. We do the same thing with the y components. The tip of the arrow has an x coordinate and a y coordinate. The y coordinate is the y component. And we can also imagine projecting that vector, the shadow it projects onto the y-axis. That's the same thing as the y component or the y coordinate. All the same. And here's a situation where that y component is a negative quantity. The arrow has a downwards trend. If the arrow is in quadrant 3 to the lower left or quadrant 4 to the lower right, the y component is negative, and we have to be ready to be able to handle those situations. When we talk about the direction of a vector, first off, we often use the lowercase Greek letter theta to represent it. In rare situations where there are multiple angles, we might use the lowercase Greek letter phi. which is the circle with the vertical arrow through it, or the letter psi, which looks like it's a letter that's trying to fly off. I strongly recommend measuring all of your angles with respect to the positive x-axis. This is that one-size-fits-all approach that I emphasize. Measure all of your angles with respect to the positive x-axis. Sometimes you might say that's annoying to do, but I think in the long run, even if it's annoying, it saves you time in the long run, because that way you won't make any mistakes about whether you should use cosine or sine or something like that, as we shall see. But measure your angle theta, the angle the vector makes, with respect to the positive x-axis. At least that's how I'm going to encourage you, and that's how I am going to report my angles. All of these angles measured with respect to the positive x-axis. So the angle is measured with respect to the positive x-axis. The magnitude, remember we have a vector, so we have to worry about magnitude and direction. The magnitude is kind of like the size of the vector. On the screen we see a couple of vectors, one represented by a long arrow, the other represented by a short arrow. Presumably, the long arrow represents a vector with a relatively large magnitude, and the short arrow represents a different vector with a relatively small magnitude. Magnitude has no direction, and the magnitude is like an absolute value. Magnitude is a size, and that means that we always treat it as a positive quantity. So the magnitude of the vector is always a positive quantity. It's the direction that could be, that tells us whether it's in quadrants 1, 2, 3, or 4. Now suppose we know the magnitude of the vector and we know the angle theta the vector makes with respect to the positive x-axis. Let's say the magnitude of the vector is represented by capital A and the angle, of course, represented by theta. If your angle theta is measured with respect to the positive x-axis, your x component is always A times cosine theta. Always, always, always. Make sure your angle is measured with respect to the positive x-axis. Cosine gives you the x component. Period. End of sentence. If you want the y component, if your angle is measured with respect to the positive x-axis, your y component is always going to be via sine. And y component would be A times the sine of theta. Always sine for the y component if your angle is measured with respect to the positive x-axis. These x and y components can be written out in a format like you see typically in the first equation. You see the vector A. We know it's a vector because it has that half arrow above it. And we see it's equal to A subscript x, x hat, plus A subscript y, y hat. And then if there were a third dimension, but there won't be, don't worry about a third dimension at this point. That becomes more important in Physics 150. But in Physics 140, don't worry about a third dimension. We have the x component of the vector represented by A subscript x. We have the y component of the vector represented by A subscript y. The x hat is just simply an indicator. It just tells you this is the x component. Whatever is in front of the x hat is the x component. And whatever is immediately in front of the y hat is the y component. The x hat and the y hat serve no other purpose than to identify whether the preceding quantity is an x component or a y component. Don't read anything else into x hat and the y hat. The bottom line with I hat, j hat, and k hat, that's what engineers do. I don't know why. I blame the Germans. Okay. Vector arithmetic. At this point in time, we have looked at how to take magnitude and direction and convert it into x component and y component. Later we'll look at x component and y component and converting it to magnitude and direction. But let's just cleanse the palate a little bit and make sure we understand how math works with vectors. If I take a vector and I multiply it by a scalar quantity, that scalar quantity multiplies each component of the vector separately. An equation that we'll see later this semester, the net force acting on an object equals the mass of the object times the acceleration of the object. Mass is a scalar quantity, acceleration is a vector quantity. So when I do the number crunching, I have to take the mass and I have to multiply it by the x component of the acceleration, and that gives me the x component of the product. I have to take the mass and multiply it by the y component of the acceleration, and that gives me the y component of the product. So the scalar quantity multiplies each component of a vector. You don't break up the scalar quantity, it remains what it is. You just multiply it by the x component, and you multiply it separately by the y component. When you add vectors together, you add the x components together, and you add the y components together. You never, ever, ever, never add an x component to a y component. Please don't ever do that. There's no situation where you ever want to add an x component directly to a y component. It does not give you anything. So if you add two vectors together, a and b, you have to add the x component of a to the x component of b to get the x component of the sum. Separately, you add the y component of a to the y component of b to get the y component of the sum. And you treat those sums separately from each other. The x component of the sum is treated separately from the y component of the sum. Very similarly, if you have to subtract vectors, you subtract the x components separately from subtracting the y components. So if we're saying that the net vector is equal to vector A minus vector B, we do x component of A minus x component of B to get the x component of the difference. We do the y component of A minus the y component of B to get the y component of the difference. Treat x stuff separately from y stuff when you add and subtract vectors. Okay. Back to the main thrust of this lecture. Now that we have at our disposal the ability to take the magnitude and the direction, and from it get the x component and the y component, we need to go in the opposite direction. Given the x component and the y component, how do we find the magnitude of the vector? Well, the magnitude is not so bad. The Pythagorean theorem actually tells us how to calculate the magnitude of a vector. You take the x component, you square it, and you take the y component and you square it, and you add those squares together, and you take the square root of that sum. That's like saying a squared plus b squared equals c squared, where c squared is, where c is the magnitude of the vector, a is like the x component, and b is like the y component. In the bottom part, just beneath rule 4, we imagine a vector with an x component of -6 and a y component of 5.2. So we take -6 and we square it, we get 36. We take 5.2 squared, and we get, 27.04. And we take 36, we add 27.04, we get 63.04. So the magnitude of this vector is the square root of 63.04, which I calculated to be 7.9. So there's the magnitude of the vector. X component squared plus y component squared, take the square root. To find the magnitude, you Pythagorize the x and y components. And then the direction. Now this is kind of the tricky one. But if I'm given the x component and the y component of the vector, if I want to find the direction, nominally, I just say the inverse tangent of y component divided by x component. So take the y component divided by the x component, and then I do the inverse tangent of that quotient, and I should get theta. That's how it's supposed to work. In theory, that's how it does work. But you're going to be doing these calculations on a calculator, and things get sticky. Calculators, I don't know what's going on with them. I wish I could blame the Germans, but I have a feeling it's Americans who are responsible. But I blame engineers. Because suppose you have a vector that's in quadrant 2, or for that matter, a vector in quadrant 3. Whether it's in quadrant 2 or quadrant 3, your vector has a negative x component. So this is where your calculator blows up. This is where your calculator fails. If the x component of your vector is negative, your calculator is going to be wrong. What's going to happen is your calculator is going to give you an answer that is pointing in exactly the opposite direction. I don't know why they're programmed this way, but they are. Calculators are programmed so that the inverse tangent function always gives a value between negative 90 degrees and positive 90 degrees. That means anything in quadrant 4 or quadrant 1, anything to the right of the y-axis, whether above or below the x-axis. If your vector is pointing in quadrant 2 or quadrant 3, the calculator is going to give you exactly the wrong answer. Fortunately, the answer is exactly wrong. And because it is exactly wrong, if your vector is in quadrant 2 or quadrant 3, use your calculator, get the result, but then add 180 degrees to the calculator's result. If your vector is in quadrant 2 or quadrant 3, when you do inverse tangent, take that result, add 180 degrees. So, make sure you pay attention to detail. Sketch the vectors. If you don't sketch the vectors, you better have a good imagination, which means sketch the vectors. Now, if you don't sketch the vectors, as it says, then you run the risk of trusting your calculator. Don't blindly trust your calculator. There should always be some sort of corroboration for any results on your calculator. And if your different methods don't agree with each other, you've got to figure out what's happening. This is one of those issues where it can happen. If you know that your x component is negative, then you should know that your calculator will give you exactly the wrong answer. So if your vector is in quadrant 2 or quadrant 3 where the x component is negative, your calculator is going to be wrong, but exactly wrong. Run through the calculation. Let's see what the calculator says, and then if your vector is in quadrant 2 or quadrant 3, if your vector has a negative x component, take that calculator answer and add 180 degrees. That will give you the true value of theta for that vector. Keep in mind that theta is measured with respect to the positive x-axis. And that's the review. I hope it's not been too intense, and of course we'll be discussing this further in class. Bye-bye.